Hi everyone. Today we are presenting our project on reusing exploit attack detection using machine learning. So our team data defenders includes me, Sam, and Renushri. In simple terms, our goal is to improve how systems detect cyber attacks, especially the ones that are usually missed. So this project was done as a part of our data science for cybersecurity course by team data defenders, of course. Okay. Let's go to the next slide. Yeah. So today we're going to be discussing about the problem, how uh, this exploit attacks. Then we're going to be talking about the data sets that we have used, and then we're going to be ex- discussing about the approach, and then results, and then we're going to conclude. Yeah, let's go to the next slide. Mhm. Okay. To understand our work, let's first look at the current cybersecurity landscape. Today's network attacks are not only increasing in number, but also becoming more sophisticated. A major challenge is exploit attacks, which target software vulnerabilities, including zero-day attacks that are unknown to the system. Then we have traditional detection systems which rely on known signatures, so they often fail to detect new or modified attacks, which leads to two problems. Either the system misses real attacks or it generates too many false alarms. So, our goal is to build a system that can detect attacks accurately while keeping false alerts under control. Let's go to the next slide. Now, let's quickly understand what an exploit attack is. It usually happens in four stages. First, the attacker scans the system to find weaknesses. Then they identify a vulnerability. Next, they send a malicious payload. And finally, they gain unauthorized access. And some common examples include buffer overflow, code injection, SQL injection, and zero-day attacks. So essentially, exploit attacks take advantage of system weaknesses to break in. Now let's go to the next slide. Yeah. So now the key question is, what's wrong with the existing detection systems? So traditional systems depend on predefined rules or signatures. So if an attack is new or slightly modified, the system simply won't recognize it. And they also don't learn from new data and require constant manual updates. As a result, many attacks go undetected, and these are called false negatives. And they're very dangerous in cybersecurity. So, to solve this, we use machine learning, which can learn patterns from data and detect even unseen attacks. Now, let's go to the next slide. Yeah. So, this slide shows our overall approach. We started with data analysis on the data set. Then we performed pre-processing like encoding, scaling, and handling missing values. Since the data was imbalanced, we used SMOT to balance it. After that, we trained two models, decision tree and random forest. And then finally, we evaluated them using metrics like accuracy, F1 score, and ROC AUC. All right, let's go. Yeah. Okay. Here we use the UNSWNB15 data set, which is a modern cybersecurity data set. Contains 45 features capturing different aspects of network traffic. These include things like data transfer, TCP behavior, timing information, and protocol details. The dataset has both numerical and categorical features, which makes it suitable for machine learning models. Yeah. So, uh, in this slide, one major challenge we found was class imbalance. So there are many types of attacks in the data set, but their distribution is uneven. Some attack types dominate while others are very rare. So for our problem, we simplified it into binary classification, which are attack versus normal. But even then, the imbalance remains. which can cause the model to ignore rare but important attacks. And that's why handling imbalance became very important for us. Okay, let's go to the next slide. All right. In this step, we analyzed how features relate to each other. We found that some features are highly correlated, especially those related to data size or traffic volume. This means that there is redundancy in the data. Initially, we considered using PCA to reduce the dimensions, but later we found that tree-based models like random forest can handle correlated features well. So PCA was not necessary. Okay, let's go to the next slide. Okay, so from our experiments, we found several important insights. First, uh, ensemble models like random forest performed better than a single decision tree. Second, we saw significantly reduced false negatives, meaning fewer attacks were missed. Third, improving recall was very important because detecting attacks is our priority. And we also found that feature engineering helped improve performance. And interestingly, removing PCA actually gave better results. All right, let's go to the next slide. Okay. In pre-processing, we prepared the data for modeling. We converted features into numerical form and scaled numerical values. We applied SMOT to balance the data set, but only on training data to avoid bias. We also created new features to better capture patterns in network traffic. And these steps helped us improve model performance significantly. All right, let's go to the next slide. Okay.
Yep.
Finally, let's talk about SMOT, which was very important. No, 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 the previous slide.
Um. Oh yes. Okay. Jeremy. Yeah.
No, no,
Yeah.
I'm gonna talk about the SMOT as well. So let's go to the previous slide, Sam.
Okay.
Yeah. So finally, let's talk about SMOT, which was very important in our project. SMOT stands for Synthetic Minority Oversampling Technique. So instead of simply duplicating data, it creates new synthetic examples of the minority class. This helps the model learn better patterns for rare attack cases, and as a result, it improves detection and reduces missed attacks, which is critical in cybersecurity. And now I'll hand it over to Sam, who will walk you through the modeling and the results.
Thank. Okay. Thank you, Jeremy. Hi, everybody. So now I will start to our baseline model, which is the decision tree. So our group choose decision tree because it's very easy to understand and also visualize and making it a good starting point. So and also we use the entropy as the criterion and apply class on the weighted and to penalize Mr. Take more heavy. So even like we use the tuning and a model like still struggle to like to capture the complex the attack pattern, especially if we compare to the more advanced model. So, but in our project, so the decision tree is serving mainly like the baseline and also for if, for example, like if we compare, but that one is not a final model. And also, I'm gonna move to the next slide. So our next slide, we're gonna talk about the random forest, the final model. So for the random forest, it's an ensemble method that combine the multiple choices, and I'm sorry, not multiple choice, it's multiple decision tree. So which have reduced the variance and improve the stability. So for the random forest, it can capture more complex and non-linear pattern in attack traffic. And if we compare to the single tree. So we also use that class balancing and tune parameters to improve the detection performance. So yes, and overall, I can say like random forest give us a better choice or better generalization with its very like with its like why we select to the our final model. Yep, so let's go to the next slide. So the next slide we're talking about the threshold tuning, detection versus the alert noise. So the default the threshold that of 0.35, I'm sorry, before we use 0.5. So we thought like it's a good idea for our project. But after that, we found out like that one is not ideal for security tasks. So that's why we lower from zero point 0.5 to the threshold 0.35, which is allow the model to catch more attacks. So for this model, it's very improved recall, meaning the fewer attacks are missed. However, like the trade-off is very like may increase for positive. So in our case scenario, we prioritize like reducing missed attack because the false negative are more dangerous in cyber security. Yep. So let's move on to the threshold sensitive analysis. As you guys can see, so when I do run the test and something like that, so I put the random for 0.2 until 0.5. So like I said before, as you can see, it's like 0.5. We can see like the the false negative is higher. That's why we're gonna choose like the median one. So we're gonna choose like 0.35. That is our target. So let me go to the next slide is evaluation metric that what we measure. So for that one, so accuracy show overall like correctness, but it is not enough for security tasks. So precision they tell us how many alerts are actually real attacks. But recall is very important because it measure like how many attacks we successfully detect. So we also use the F1 score to balance the precision and also recall and also the OOC and AUC to measure how well the model separate like the classes. So for example, like most importantly, we focus on a false negative. So because misattack can lead to the serious system compromise. So yes, let's move to the next slide. So decision tree result. So here, the result for that one. So it's actually like I can say like 89.07 accuracy. And also for the recall is 89%, as you guys can see. And for the OOC and AOUC is 91.23%. So for false negative, it's like 17,608. So, but however, it still produce a highest number of the false negative, like around like, for the missed attack. But so this means like many attacks are not detected. So while the model is interpretable, so its detection capability is weaker compared to the random forest. So overall, it is useful for understanding behavior, but not ideal for deployment. So let me go to the next slide. So the random forest result. So we see like improvement across the key metric. So accuracy increased like about 91.42%. So recall we improve it to 89.09%, and OOC and LUC is 98.31%. And the false negative that we're looking for is 13,017. So it means like that one is show like it's dropped. But this means like the model catch like the importantly like more attack than decision tree. So although the false negative may increase like slightly, but it is an acceptable and trade-off in a cyber security. And we go to move to the next slide. It is a model comparison with this decision tree and random forest. So as you guys can see, the random forest is clearly perform better. So it have higher recall, meaning better attack detection. It is also have a higher OIC and LUC, showing the stronger ability to distinguish between normal and attack traffic. So most importantly, so it reduces the false negative significant. So since the false negative like are the more critical risk in cybersecurity, but random forest is selected as our final model. So for the next slide, if for Renu, she gonna give the ROCQ comparison. Thank you.
Yes, up to this point, we built and trained our models for exploit detection. As my part of project, I focused on evaluation and optimization, especially analyzing how different threshold values impact recall and false negative, as discussed in the previous slide by Sam. Because in cybersecurity, it's not just about accuracy; it's about how many attacks we fail to detect. So in the next few slides, I'm going to show how our models actually perform and how we tune them to reduce real world risk. So now let's start with ROC curve. Uh, we evaluate how well each model distinguish between attack and the normal attacks across all the thresholds. The random forest achieves an AUC around 98.31% when compared to the 91.23% for the decision tree, which is almost like 6%, and it's on the positive side. This means the random forest consistently ranks attack traffic higher than the normal traffic, regardless of where we set the threshold. So overall, it gives us much stronger separation and more reliable predictions. Uh, a higher AUC means fewer uncertain decisions and more dependable detection. But strong separation alone is not enough. What really matters is what we are missing. And now let's go to the next slide. Okay, and as part of our evaluation, we specifically focused on how threshold values affect missed attacks. False negatives are the most critical errors. These are attacks that go completely undetected. By applying SMORT in a pre-processing and lowering the threshold value uh, from zero point 0.2 and zero point 0.5 to 0.35, we reduce false negatives at almost around 5,000. That's nearly 30% reduction. Additional attacks, meaning 5,000 additional attacks are now being detected. This improvement came from careful threshold tuning, not just the model choice. And while choosing this threshold value, it comes off with the trade-offs too. Sam, could you please move on to the next slide? Uh, uh, we can go to the trade-off slide, Sam. Next slide.
Next slide, Sam.
Oh, I'm
After
sorry.
key findings, next slide.
Okay, I'm sorry.
While tuning the threshold, we observed a clear trade-off that lowering the threshold value increased recall and reduced missed attacks, but it also increased false positives, meaning which means more attacks and more alerts, that false alerts, which where we have to spend our more time chasing the positive data while leaving the actual affecting negative data behind the attacks, which where the enterprises loses millions. um, so this is the trade-off that we chose to accept, because minimum alerts is okay rather than ignoring the false negatives. So based on this optimization, here is what we learned about the system. Next slide, please. So, while doing our project, here are the few challenges that we faced. False negatives are reduced but not completely eliminated. And also, optimal threshold depends on the organization's risk tolerance, and it's not like ideal. So, different environments may choose the different balances. And since the data set that we took is static. That means it doesn't have the modern type of attacks like APTs and the ransomwares, so it does not automatically adapt to evolving attack patterns and needs improvement. So, to address these limitations, we identified several improvements based on where what we clearly understood and managed. Going to the future work, to improve this system further, we can add explainability using Sharp to understand the feature importance, which we are lacking here a bit. So we can also test advanced models like XGBoost for potential performance gains. And from deployment perspective, integrating this into a SIEM system would allow real-time detection, which is much helpful for the analyst who is working on the real network data. And continuous restraining would help evolving the attack patterns. So, with that, let me summarize what we achieved. Go to the next slide, please. We developed a complete machine learning pipeline as far we discussed for exploit detection using real network data, and by applying smooth and threshold tuning we significantly reduced the missed attacks. Random forest was selected as the final model due to its strong generalization and ability to detect complex patterns. Our focus was not just accuracy but minimizing real world risk. To conclude, here is the takeaway. Uh, our decisions were purely based on improving the improving detecting the false negatives rather than optimizing the performance metrics ideally.
All right. So that brings us to the end of our presentation. In summary, we used machine learning to improve exploit attack detection, reduced false negatives, and selected random forest as our final model for the better performance. So yeah, thank you for your time and attention, and thank you for listening.
Thank you.
Bye
Signing off.
bye.